Good morning, everybody. Welcome back. Nice to be in a cool theatre today, I think. And this morning we've got, I think, the makings of a fascinating session. Decision Making, the sequel. And first up, we've got David Budescu, who's going to be giving us some insights into the psychological dimensions of decision making. So something that I personally know absolutely nothing about and really look forward to hearing more about it. Over to you, David.
Thank you very much. Can everyone hear me? Okay. So how did I get here? As I said, I'm a professor of psychology. So let me give you a little bit of an insight of my own career. I am a quantitative psychologist, which means that I was trained as a statistician and psychologist, got my PhD in quantitative psychology and psychometrics. And throughout my career, I maintained two different research paths, one to do more traditional psychometrics, measurement, and applied statistics, but also became interested in modeling human judgment and human decision-making under uncertainty. Issues as to how to best elicit probability judgments, uncertainty judgments, how people understand and communicate with each other things about uncertainty, and how do people act in the presence of uncertainty when they need to make decisions as individuals or in small groups. And in this context, I became interested, with help of some people from this room, in the issue of climate change, because climate change poses many of the prototypical issues about uncertainty. Although uncertainty, the way you think about it, is slightly different from the level at which we think about it, which is a much more lower and micro level. And so what I hope to do today is to give you a little bit of an insight of the kind of work that people in psychology are doing. And this is going to be sprinkled with some examples that are related, some of them more directly, some of them somewhat indirectly, to issues of climate change. So I have probably slides to talk 3 or 4 hours, but that's if I could talk uninterrupted. These are the things that I would cover. To say a few words of why I think this is important for this community, to give you a little bit of background and terminology, and then describing the way we think about uncertainty, and then I kind of broke it down into how people make judgments about probability, how people intercommunicate with each other probabilities, and then at the end, if I have time, something about individual decision-making under uncertainty and the effects of uncertainty about group decision-making in the context of social dilemmas, which I think was something that people were particularly interested in that. So why is it that why I think a community of scientists, climatologists, modelers should be interested in what we as psychologists are doing? And I think primarily because everything that science does needs to be translated in this context, especially, into policy, needs to be accepted, voted on, implemented, and obtain the tacit cooperation of the public at large. And so what you need to do, you need to find the effective way of communicating what you know and how much you know, how much you don't know, to people who do not necessarily understand. In fact, you can take it for granted they do not understand the science, and they have, to begin with, some relatively skeptical views of some of the things that are being communicated. So that's one component, namely to find the right way to communicate uncertainty and its nature and its magnitude to the public. The other is really, I think, part and parcel of what many modelers are doing. Many models in many domains are depending on some degree on expert judgments to quantify uncertainty and to incorporate it into the model. So you need to know ways in which people deal with uncertainty and how to best extract this information from them in order to optimize the models. And last and not least is the fact that if you get a sense of how people in general, human in general, yourself included, are thinking about uncertainty, what are the things in which you are, as I'll show you in a moment, suboptimal in some ways, will give you some further insight into how to communicate to others and how to understand and interpret what others are communicating to you. I should have said, feel free to interrupt me at any point. I'm happy to answer any any questions. So let me start with some very, very basic. Let me tell you of what this area, this community that I'm part of, is doing. So we call ourselves with two names. Some traditionally used to call ourselves the Judgment and Decision Community, JDM. Recently, it has become more fashionable to refer to ourselves as BDM, Behavioral Decision Making, and to take out the judgment. What we are doing mostly experimental work that deals with the way decision makers are making decisions, individuals or in small groups. If people ask you ask me to map where we are in the psychology, we are basically at the intersection of cognitive psychology and social psychology, in the sense that even things that we study about individuals are typically embedded in some kind of social context much more than the typical cognitive psychology work, which is about reaction time and perception and attention, and focuses on reaction times of milliseconds. That's not the kind of work we are doing. We're doing more about deliberate decisions in some context, sometimes by individuals, sometimes in context of groups. And the way we think about models of decision, there's a sharp distinction, which is, of course, sharper on paper than it is in practice, between a normative and descriptive model. So a normative model, in our language, is a model of the decision task. So if you have a particular decision problem, that's typically the kind of decision-making that anyone will learn in an decision analysis or OR, operation research context. There are a particular set of constraints, there are certain input parameters, there's an objective function to be optimized, and then using the appropriate mathematical tools, you find out the optimal solution. Quite often, in our context, the optimal solution is embedded or is anchored in an axiomatic foundation. And the typical example, which I hope many of you are familiar with, is the expected utility or the subjective expected utility model. So you're talking about a situation where people need to express preferences in the presence of uncertainties that's quantified by a probability distribution. And the theory goes as follows. If you obey a certain set of requirements or axioms, which the thing can go any rational person should accept, such as monotonicity in outcomes, intransitivity of preferences, independence between belief and actions, and a couple of other technical things. So if you accept all these as basic tenets of behavior, then it's possible to prove mathematically that your preferences can be mapped into a utility function, which is unique up to a positive linear transformation. And it also follows from that whenever you're faced between a choice between two risky gambles or risky options or risky distribution, you'll choose the one that has the higher expected utility, period. So this is a model, if you think about it, which very, very makes a lot of sense because it describes what does rational means, okay? Complete preferences, transitive preferences, and so on. And it also provides a prescription for taking all the actions. It was all based on the input. It was all based on what it is that you want to achieve. What was never mentioned in this context was not one word about the people or the entity that makes the decision maker. It was not a model of the decision maker, but the model of the decision-making problem. Descriptive or behavioral models are actually models of how people actually make decisions. In other words, they are observed, people are faced in experimental or in laboratory or in field context with choices of the same type that this model is trying to predict. And you are actually capturing the nature of preferences, the intensity of preferences, and how things are being chosen. And clearly, since it's an observer of people who make decisions, it's not restricted by the axioms. People are paying attention, are influenced by things that in the process of abstraction into building an axiomatic model are excluded. Okay? So the two models are not going to necessarily lead to the same conclusion in all cases. People quite often are going to make choices that violate expected utility or similar models. And much of the work that we are doing, it's really about trying to understand, identify the discrepancies between these two, and to try to understand what are the underlying processes that induce these processes, these differences. Let me give you just an example to give you a sense of what I mean. There's a phenomenon that we refer to as preference reversal. And preference reversal is, refers to the following situation. You have to choose between two gambles. So in our world, simple gambles, monetary gambles are basically just like a fruit fly in genetics. It's a kind of a basic elementary way of describing choices between uncertain outcomes, and you can always abstract and strip away any context, and simply you can win X dollars with P, and you can lose Y dollars with 1 minus P, and then another one, and choose between them. So there are situations where you ask people, would you prefer gamble A or gamble B? And they say gamble A. And then rather than presenting the two side by side, you present each one of them separately, and you ask people, well, this is a gamble that gives you a certain outcome with a certain probability. We would like to buy it from you. How much would you require in returns? What's the cash equivalent of this gamble? And what you find is that in situations we can characterize quite clearly, people may prefer A over B, but require a higher cash equivalent for B than A. So in other words, their preferences as they are expressed and manifested in their behavior are not consistent with the notion that things have a utility and an intrinsic value, because clearly you value the same gambles differently when they are presented in a comparative fashion or they are presented individually. This would never be in line with any normative model, right? But it is exactly what the kind of thing that we are looking at. So we have a very mixed view about what probability is. So like everyone else, we agree that we think that we understand probability mathematically in the calculus of probabilities and calculus of uncertainties. But when you talk to people and say, can you explain to me what probability is without using the word probability? Describe it in other way. And how do you think? What does it mean to you when I'm telling you, I think this event has probability of 0.73? And we have the three typical interpretation of probability. The classical Laplacian probability that only applies to things that to begin with have equal probability, like all the games of chance, spinning a roulette, tossing a coin, rolling a dice. There are 2, 4, 37 basic events which we assume in a Laplacian fashion that they are equiprobable. So you see the circularity here, and therefore we can define probability of any event based on that. The dominant view is the frequentist view. It's essentially that probabilities are long-term relative frequency, as in a life table, right? It tells you, all the people born in a certain year, how many of them will live to be 73 years old, and so on. And they depend on repeated observation of the same event, and supposedly under similar events. So at the end of the day, you can think of this as an objective probability, so that you can talk about the probability of event E is, followed by a number, because it is probability that is clearly associated to the event, and everyone would agree to it. And the third one is really the subjective probability notion, which is kind of a definite savage idea, which talks about probability being not something that everyone can agree on observe, but probability being a level of belief in a truth of a certain statement or in the occurrence of a certain event, which is personal, based, and conditional upon what everyone, the target person knows about that event at a given point in time. So now the statement is not that the probability of event is, but that my probability of event is, and there's absolutely no requirement that different people would agree on that. So in some cases, it's quite obvious and uncontroversial which interpretation is relevant. In some places, interpretations are very, very mixed and combined, and different people may not even agree on which one to apply to a particular context. And in some cases, things are mixed altogether. And so here's an example. We have models, climate models, for example, that generate probabilities of events. How do you think of these probabilities in this context? So you can say, well, I'm running this model, and these are these parameters, but I'm running it thousands and thousands of times with different initial conditions and different variations, and I find this event occurs in a certain proportion of the time. So you can think of it as being a kind of a frequentist objective probability. But every single event of this type, every single model that generates that probability is in some sense subjective. It is based on a particular instantiation of a model with a different set of parameters, and therefore the beliefs that you're generating through the model are a function of how confident and how strongly do you believe in the actual model that is generating it. So it's not quite clear whether the probabilities that are generated by a model should conceptually be thought as being objective or subjective. We distinguish between, well, there are many typologies or taxonomies of the various sources of uncertainty. And many of them are just repeats of each other with slightly different names. This is just one we may have come up earlier between what we call external, which means strictly based on the environment and not under the person's control. The external aleatory events, so all games of chance or obtaining genetics and things of that type, which are all can be characterized typically through distributions. So this is one type of uncertainty. That's an uncertainty about the outside world. And the other one is internal or epistemic. It's a reflection of one's knowledge or lack of knowledge or incomplete knowledge about that event. So for example, if you ask people, which of the two, do you think that, think of Peru and Chile, which one has a higher population? I would say Chile. How confident, what's the probability that you are right? Okay, so you're asking me about the probability, which is subjective. It's about my level of knowledge, and I need to come up with a way of generating this number. That is what I mean epistemic internal. It's a reflection of how much do I know and how sure I am about what I know. So another distinction, so it's interesting that if you are looking at people making judgments of this type about how much they know and so on, and you look at the distribution of numbers or probabilities they generate, quite often you get a W-shaped distribution. In other words, with large concentration, people at 0, 1, and admissions, I have no idea, which is around 0.5. So the three modes, 0, 0.5, and 1. And again, the distinction between the various cases is not always very clear. It may come up again in a couple of examples later. Here are some sources of imprecision and in probabilities and uncertainty, which may be the basis for inability, or not inability, but imperfect communication between different people. The first thing, which in my opinion is kind of underestimated and underappreciated, is the nature of the events themselves to which we assign probabilities. So strictly speaking, what you'd like to assign probabilities is to unambiguous events which are understood equally well and identically by everyone. But quite often, the events to which probability are assigned are ambiguous, at least to some degree, in a sense that they open the door for various people to interpret them in different ways. So that's one explanation. The second one is the nature of the uncertainty. What are the sources that go into making an event uncertain? Okay, how precise and imprecise they are. And the third one is the language that one chooses to communicate probabilities to others. So I can say this event has a probability of 0.3, or I can say it has a probability between 0.2 and 0.4, which is an imprecise numerical value. Or I can use some kind of fuzzy statement, say, it's quite high, or it's unlikely, okay, which is in itself imprecise. So each one of these three sources are contributing potentially to miscommunications or misunderstanding. And later on, I'm going to talk a little bit about the relationship between the three and how to try to optimize communication in light of this. So now I'm going to talk about, to the second stage, which is about judgments of probability. How do we get people to communicate to us, experts or non-experts, probability? So I'm going to make a distinction between discrete events, which is assigning probability to a small number of events, or continuous distribution. I'm going to make a distinction between direct and indirect methods and give you some examples. So clearly the one that's most often done is ask people for probabilities of discrete event. What is the probability that event A will happen? And so that's what this is essentially what I'm calling two categories, C equal to, because it happens or it doesn't. And the full and half or half range distinction is essentially you can ask people, what do you think the probability that Cincinnati has a higher population than Cleveland? And people will give you a number between 0 and 1. Or you can say that I gave a previous example, which one is more popular, Cincinnati or Cleveland? And once you've selected one, then say, what's the probability? Clearly, I don't expect it to be from 0 to 1, but rather from 0.5 to 1. And here's an example how this is implemented. This is, in the last 4 or 5 years, I've been very involved in an issue of using public forecast for lot of geopolitical events, and this is from our project. So this is a question that we ask thousands of people who are on our website, one of many, many questions. The average mortgage rate for a 30 years fixed rate loan in the US will be above 4.5 before March 30, 2012. You see how carefully we are. This is an unambiguous event. No two people can understand this in different ways. But if you say by the end of spring, that would already be somewhat ambiguous. Okay. So once they make, so that's the event, and then people are asked to make a prediction. In this case, the guy says no, it will not occur, and then to assign a probability. In this case, what they are doing, where the probability is actually expressed by moving the sliders. Right? And as you move the slider, the numbers also change. And the reason we use sliders rather than numbers is because there's a very strong phenomenon in making things of that type of edge aversion. People do not like to say things very close to 0, very close to 100 or 1. And when there's a response doesn't actually call for number, but simply by pulling the sliders, this is somewhat reduced. So in this case, we have everything. We have both numbers and sliders, and we have both a categorical prediction, So that's what this would look like. You may ask yourself, why do you ask for both? It will occur, it will not occur. Don't they add up to 100? The answer is yes, of course they do. But we also have questions in instances of that type where the number of events that are being predicted are not 2, but for example, of these 4 candidates for president of Argentina, which one, what's the probability that each one will be selected, and then you need to have 4 people, and then you need to have 4 slider, and we wanted to have a uniform format. Okay. Here I'm looking for a continuous distribution. So for example, there's a phenomenon of interest, could be time, could be money, could be temperature, X, that has a cumulative distribution. And on these 2 slides, you have the same, the function is the same, the cumulative, the CDF is the same, X and f of X. But we can make this kind of judgment in 2 different ways. We can do what we call a fixed value event and fixed probability event. So what I mean by that is the following. What you want to obtain, of course, is a number of points on the curve from which then you could be able to actually fit the curve. Now, the way you can obtain this number by saying, for this X, tell me what is the corresponding fx. For this X, what is the corresponding fx? So you start with various events, and then you ask people to make judgments of probabilities, or you can go the other way. Please give me the temperature such that there's a probability of 0.75 that tomorrow will be warmer or colder, and then so I'm starting with probabilities, and you need to give me values. Okay, so you can start for different values. You can ask people to communicate judgment. So these things are in some sense interchangeable. You would expect them to give the same results, but people actually find it much, much easier and more natural to make this kind of judgment, to start from numerical values and generate probabilities rather than the other way around. But they are not very different. Here's some data, an example. Oh, I'm sorry, before I show an example. And you don't have to ask, I talked about direct and indirect. You don't have to ask people, what is the probability there? You can infer probabilities from asking them to make judgments of this type. So this is from a study that Ali Abbas and I did with graduate students at Stanford, and they were predicting the temperature on a particular day in December, 10 days away or 12 days away from the moment this was done. And essentially you ask them a question of this type. Well, you can win $20 if the temperature is going to be less than 25, or if when we spin this, it will land on orange. Okay? So which one would you rather bet on? From which we assume, since we assume that you are rational and you have a utility function for money, which is invariant across the sources of what generates your income, that you're going to put your money on the one that is more probable. So if you say that this is more probable, then what we can immediately do is adjust either show another pie with a different composition, not than 50-50, 40-60, or 60-40, or change the number of degrees to 24, 23, and so on and so forth. You can get a bunch of repeated iterative questions of this type where people only have to say, I prefer this one, until they reach a point of indifference, and then, so you know that the probability of this event matches exactly the probability on the probability wheel. And these are some examples from four of our participants selected, not at random, where you see that there are two curves on each one of these four panels, and in one case, one of them is a curve based on fixing probability and judging quantity. The other one is based on fixing quantities and judging probabilities. In some cases, they are almost identical. In some cases, they are slightly more different, and so on. So, in general, in this case, the subjects were very good, participants were very good, and the fit was very, very, very similar. But that's the kind of judgment. This is the kind of expert elicitation that you can easily do. So in this case, what you can see here, we fit beta distributions to each one of them, and this is just another way for each one of them have the parameters of the best fitting beta distributions. There are other methods. I want to show you one other one, which is a favorite of mine, which is the reason I like it is because it's a way of asking people about probabilities without ever using the word probability. So essentially, what you ask people to do is to compare in a pairwise fashion possible events, and you ask them which one you think is more likely and how much more likely. Okay, so here's an example from my former student Han Hui's dissertation. In this case, there are 4 events. They refer to the joint distribution of smoking and having cancer. So S is smoking, C means cancer, and you have 4 joint events: smoke and cancer, smoke and non-cancer, and so on. And every judge is making all the 6 possible pairs. Which is more likely that someone will be smoking and not having cancer, or not smoking and having cancer? And they use a slider to say this one is 7 times more likely. So for every pair, you determine which one is more likely and by how much, and you generate this matrix, which is a positive and reciprocal matrix. The diagonal is always 1 because that's event in itself, so it's by fiat 1. And you see that everything which is on both sides of the diagonal are multiplied to 1. They are reciprocals of each other: 3.3 and 3, 0.14 and 7, and so on. So we have 4 events, 1, 2, 3, 4, but we have excess judgments. We have 6 pairs. So people are generating all these judgments, and then what we are doing, so people never said a word, they never heard a word about probabilities. Which is more likely and how much more likely? And then you take the geometric means of every row, you normalize them to add up to 1, and you come up with the events of each one of them, the probability of each one of the events. So in this case, not smoking and not having cancer is judged to be 0.65. This is smoking and cancer is 0.25. So these are subjective judgments. They are not necessarily the objective one, but that's just a way to extract from people information of probability without ever mentioning the word probability. How would you know that probability judgments generated by experts or friends or whatever are good? What are the criteria for determining the quality of these results. So Tom Watson and I wrote a big review on management science in 1983 about this. Much of the literature over there is outdated by now, but I think that these things that we've identified are still very valid, and I don't know of any alternative list of things to look at. One, you would expect judgments to be reliable and stable. In other words, if you repeat them over time, everything else being equal, you expect them to be similar to each other, not to be widely different. Secondly, you expect coherence in two different senses. You expect coherence in a static sense. For example, you expect that binary additivity, the probability of A and probability not A, will add up to 1. You expect they will satisfy all kinds of internal requirements, such as the Fréchet bounds in probability. Does everyone know what the Fréchet bounds are? For any probability distribution, the probability of A and B is bounded from above and below. The joint probability of A and B cannot be larger than the max of PA and PB. And the mean of 1 PA plus B minus 1. That is true. That is called, they're called a Fréchet bound. Essentially, basically saying joint probabilities are not totally independent of the marginal probability that govern them. So that's kind of sense. So you want people to make this kind of judgment, and you want them to obey them. They don't always do. Linda, the famous Linda. Linda is. Do you know Linda? You know her? So I don't have to tell you about her. All right, so I want. But Linda is what? You don't know her? Okay, so you know a different Linda. Oh. I am kind of slow. I'm sorry. It's not you. So you read a vignette of 4 or 5 sentences about Linda, who is, she graduated, she went to college and she graduated in social studies, and she was very active in all kinds of social events and social causes, and she was active in the feminist movement and so on. So you get a picture, you can envision her. And then you ask a bunch of questions about Linda. For example, how likely it is that Linda is still active in the feminist movement? How likely is that Linda is a bank teller? And many others. And one of them is how likely is that Linda is a bank teller and active in the feminist movement. Okay? So what you have situation, so in that case you have a situation where the judgment that she is a bank teller and feminist is judged as more likely than she is a bank teller. In other words, the conjunction of two events, okay, is judged in violation of a Fréchet bound as more likely than each one of the constituent events. And later on, I'll give you an explanation of what that could happen. The other thing that you'd expect, the other thing is dynamic coherence. In other words, that when people are getting new information, they need to revise or update their probabilities, you want this to be, again, consistent with the nature of the data. So for example, if someone thinks that event A is more likely than B and they get new evidence supportive of A, you would not want them to revise their probability judgments in the opposite direction. Converging validity is basically just a statement that you have many procedures to estimate the same probability, you'd like them to converge the same value. Now, this is a list that everyone should agree with, including all the subjectivists, because it is all about how your beliefs are coherent, self-consistent. These two, which are validity and calibration, are about the relationship between your beliefs and the true reality. And that's, so for example, if you make many judgments, and these events actually materialize, we can correlate or somehow look at how close your predictions are to the occurrence. So you are comparing the probabilities with events that occur or not. But that's something, for example, that a subjectivist rejects offhand. The first chapter, just a second. First chapter in Definitive's book, he said, probabilities do not exist. Probabilities do not exist in any sense that they will be comparable across people. They are subjective and personal. Therefore, there's absolutely no point in questioning whether my personal beliefs about someone getting sick or someone winning the elections actually match reality, this is not a valid test for a subjective probability. Okay, I'm sorry.
I'm just curious as to whether or not these criteria apply to judging the credibility of experts. Mm-hmm. So if an expert is providing reliable, stable advice, internally consistent, coherent,
sure,
and draws on multiple lines of evidence, are those criteria that one might use to say, there we have a credible expert?
No, I think that these criteria should be thought of as being necessary conditions, not necessarily. So I think that you would like every single an expert to have to satisfy them. They are not the whole story. I think of those as being necessary conditions. And in fact, you know, as I said, I distinguish between us who do the theoretical, the empirical work on JDM, and people who do the more normative models. There's a third branch in this group, which is people who do decision analysis. People who are actually working with decision makers in industries and other cases, and they help them basically structure and make decisions of this type. And a good portion of what a good decision analyst would do is that he or she would work with the decision makers to establish that they are comfortable enough with the procedure so that they can display all these, and only then they begin to take seriously their judgments. Okay? So I want to say a few words about this calibration, because calibration is basically the most popular and the most often used notion of goodness of probability judgments. And what I'm showing you here is a calibration curve, very, very famous calibration curve. It's about time we get a new one that was published in the 80s. And this is a summary of weather forecasters in Chicago, and this is a summary of their precipitation predictions with a 24-hour horizon. So what you have here is the probability they assigned to rain, 0.1 and so on. What you have here is the relative frequency of occurrence. So for example, if you look at all the days in which they said it's 80%, the probability of precipitation is 80%, all these days, and there are 109 in this case, what proportion of these days it actually rained, okay? And so if someone is calibrated, you'd expect all the points to lie along the diagonal. So when I say 60%, it should happen 60% of the time. When I say 28%, it should happen 28% of the time. This empirical curve is as close to calibration that you'll ever see. It is really very well calibrated. And so what you see, and it gives you a sense of how well the probabilities judged are matching with reality. In this case, actually, it rains in about one quarter of the days, 0.25. So if I wanted to be perfectly calibrated, for example, if you'd say, hire me to predict the outcomes, the results of all the games that are going to be played in, say, a football league, in a Premier League in England next season, okay? And I'm going to say for every single game whether the home team or the away teams wins. I could say, for every single game, home team wins 57% of the time. Just as this meteorologist could say, it will rain 0.25% of the time. I would be perfectly calibrated, because no matter who's playing, I say 56%, 56%. At the end of the season, on average, 56% of the games are won by the home team. So I would be totally calibrated in this sense. I would be totally uninformative, because I have absolutely no notion of discrimination between the days in which the games who were won by the home team or not, or between the rainy and the rainy days and the non-raining days. And therefore, what we have, and I will not have time to get into this decomposition, is this notion that the calibration can really be broken down into things that have to do with how difficult it is to predict this event, because some events are really easy to predict because they occur 95% of the time. So if you say all the time, yes, 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 you usually get it right. It's how well they are calibrated, as we just discussed, but also how differentiated they are, in the sense that you assign higher probabilities to events that occur versus events that do not occur. There's another way to just look at the same things. These are the same data. But now the data are presented in a different way. These are all the events, these are the distribution. This is the distribution to all of rain for the days in which it actually rained, 25% of them. That's the distribution of probabilities when days in which it did not rain. Ideally, what you'd like to have people say, 1, 1, 1, 1, 0, 0, 0, 0, and that you have this kind of slope. In practice, what you see that the average probability assigned on rainy days is 0.58. The average probability assigned to non-rainy days, it's 0.28. So that's the kind of discrimination. So these are all various ways for us to judge how well these probabilities are discriminating, how discriminating judges are. So these are also tools to choose among alternative advisors because you can quantify them in this way. Now I'm going a little bit into psychology. So forget about weather forecasters. What do normal people, when they are asked to make judgments of this type, probability judgments, what do they find? And there are at least 5 possible patterns of the calibration curve that you can expect. Each one of them has a name. So A is over-prediction, because in this case, you always assign higher probabilities than actual occurrence. This is an under-prediction. Then you could have perfect calibrated, and you can have curves like this one, C and D, that are situations where you basically get either people that are too extreme or under extreme. And what you have, the stylized fact that what you get in real data is that people are overconfident. Okay, you have this over-extremity, which something that's typically that looks like that. So this is what, when you hear people talk about the overconfidence, that's then the idea. The idea is that when you say it's 80%, there's a chance of 80% it will happen, it actually happens 59%. So that you predict more extreme, closer to 1 for high, closer to 0 for low events. I'm going to skip this one. And what we do as psychologists, we come up with theories. Why could that happen? Does it have to do with being kind of an overall optimism tendency, something about personality and tendency to respond, something about this notion that when you're asking to make judgments of event occurring, you are over-emphasizing or putting much more interest in confirming evidence rather than disconfirming evidence. There's this notion about whether this is something that is kind of evolutionary adaptive, because, which I don't have time to explain, or is it simply a statistical artifact of the way that we are doing, basically that people are quite good at making the judgments, but all their judgments are perturbed by random error, and since probability are bounded by 0, 1, the error distribution must be necessarily skewed toward the center, kind of a regression to the mean kind of argument. And therefore, if you err, you're going to err in one direction. So I'm not going to talk about this, but I just wanted to give you a sense of the kind of work that these are doing. Here's a list. Here's a list of things that affect the way people make probability judgment. And it's an incomplete list, of course. And it is divided into cognitive, motivational, and structural components. So the first list, which is the one that's most famous and most often quoted in many, many examples, is the notion that people are making probability judgments by invoking some kind of heuristic, ideas, processes that are really easy to implement. They rely on cues from the environment. And these heuristics are, for the most part, work well, because otherwise they would really never survive. But in certain cases, they fail. And so you find problems in cases where the heuristics are inadequate. So I'll give you some example later, but they are representativeness, availability, anchoring, and adjustment. So anchoring and adjustment, for example, is that to come up with an immediate starting point, an anchor, and then you think about, but it should go higher or lower because, but the adjustment process is always insufficient. So you change in the right direction, but not sufficiently so, and therefore don't go to this extreme. The motivational are a slightly different sense of things, processes that affect. One is desirability. So there's a very, very well-known result. People always over-predict the probability of their favorite teams winning games, their favorite candidates winning elections, and so on and so forth. So in other words, basically you are, so the natural way to interpret this is that you desire this to be. So people overestimate the probability they will have a good marriage and a good career. I don't want to disappoint anyone, but and so on, and underestimate the probability of I'll have cancer, I'll get divorced, blah blah blah. So basically, that could be a wishful thinking kind of argument, but it doesn't have to be. It's not necessary. I mean, it's typically presented as such as one, but it also has to be with information. So, for example, I may overestimate what's the probability that the Pittsburgh Steelers are going to win every football game because I know so much about them. I know about them much more than I know about the other teams. And I can think of all these instances where, when despite all odds and in spite of what everyone says, they won the game. So it could be not purely motivational. It could also be an asymmetry in information. Why do 85% of the people think they are better drivers than the other on the road? Now, let's think about it. So that's clearly an overestimate. At the population level cannot work. But why can every one of us make this claim quite, I think, confidently? Because you know all the things that you're doing to be a good driver, and you know practically nothing about most of the others. I mean, you know your wife is a terrible driver, but for most other people, you don't know very much. And then think about it. If you drive an hour or 2 and 3, what do you remember at the end of the day about the other drivers? The thousands of drivers who passed you by, there's absolutely nothing to remember. But 1 or 2 cut you, or they stopped, or they didn't turn the signal. And what you remember, you have a selective sample of negative instances about other people's driving. And so that's all it takes. A little bit of knowing more about yourself and having a biased sample of behavior of others that would cause you to make this inference that you are much better than the other. Other things I mentioned already, this notion that confirmation or motivated reasoning, namely that if you have certain prior beliefs, you are bound to interpret any new evidence in light of your existing beliefs already, and you're going to therefore pay much more attention, consider much more seriously, and overweight things which are consistent with your expectations and belief, and discount or dismiss maybe sometimes things which are inconsistent. And there's this notion of affect, the emotion, how bad or good the outcomes are. And then there are issues that have to do with the structuring of the problem. In other words, how it is packed, how it is presented, how it is framed. And this issue of packing and unpacking is very interesting. It refers to the level or the modularity at which you are presenting events. So imagine the following experiment. You ask people to judge what is the probability in the general population of someone dying from natural causes or from not natural causes. So, and depending on how much detail you add to what natural causes means and what unnatural causes is, you can affect the probability judgment that you get. So if you just say natural causes or non-natural causes, it's 1. But you can say for natural causes, you can say heart disease, cancer, other disease. So the more you are unpacking the event into its consistent, because natural causes, it's a union of multiple events. The more you are spelling out the various components, the more likely, the higher the probability it will be assigned to that event. So the level of modularity or packing and unpacking. That's something that I've always had a problem. This is something that bothers me for one day I'm going to do this work. If you look at probability maps, so for example, people do probability weather forecasts. They have these maps which are like probability of precipitation. This is the contour of 80%, that's contour of 90%, and they use different colors. The choice of colors is purely arbitrary. Is there a particular set of colors? And I don't know the answer. That's the hypothesis I have. There are a particular set of colors that would cause people to look at those maps and interpret their, the probabilities in different way. There's also a claim, which for the most part is substantiated, but not always, that people are doing much better when the probabilistic information is not presented in a normed probability, in other words, a number between 0 or 1 or 0 and 100, but rather in terms of natural frequencies, counts. And the example is, people are notoriously bad at making Bayesian judgments. So, you tell them the following story. A woman goes to a mammogram, the proportion of women in the population that have breast cancer is, I think it's 8%. The mammogram has these probabilities of correct identification, this probability of a false alarm. The mammogram is positive. What is the probability that she has cancer? And I don't remember the exact numbers, but when the correct number is, if you use Bayes' theorems, around 0.45, because it has a relatively high false rate, false alarm rate. Most people clearly, widely overestimate it. But if you tell the story in a different way, it's like there are 1,000 women. Out of 1,000 women, 70 have breast cancer. Here's this test, and of 1,000 people, of the 930 women who are healthy, the test identifies so many as being sick and so on. And you actually, furthermore, you can present a grid with colored different colors for people who are sick and people who are not. People answer these questions much better. So the argument is that really it has to do with the natural frequencies and the count, because that's the way we experience life. We experience life that, oh, no, that's not, you don't run across 60% events. You run across an event again. So, I've been riding this train 100 days now. 60 of these 100 days, it was on time. So that's how the probabilities are generated. So therefore, this is a more consistent, superior mode. How am I doing on time? Until my break? Okay, all right. So I'm going to skip some of these things. This is just to show you what wisdom of the crowds means in probability judgments. So these are, we reanalyzed data that we got from our Swedish college, Peter Jaslin, where they had several hundred Swedish students make probability judgments about a variety of events about Sweden. And if you look at the calibration curve, which I described earlier, this is what you get. This is the average judges. So you see, they are quite close to being calibrated, but not quite. Now, what we are doing here, we are saying, well, can we get more information if instead of looking at individual judges, we were to combine them? So what you do, you randomly select pairs, you pair them, you calculate the average probability of the pairs, and then you get the calibration curve of the 30 pairs. And then you take quadruples and octuples and so on. And what you see, so this is basically this curve right here, the last one, is taking the average of 60 people. So what you see is that you're averaging, or you're combining, so-called wisdom of the crowd. The calibration curve begins to approach a step function, which basically says that it has almost extreme discrimination, because whenever the average probability judgment is less than 0.5, the event never happens. Whenever the average probability judgment is about 0.5, the event always happens. So this is what you can get from combining probabilities. I'm going to... All right, so let me say a few words about this. I talked about earlier about these three sources, precision of the event, precision of the probability, and of the communicating language. In general, people have this dual and somewhat conflicting preference. They prefer to communicate to others imprecisely, and they would like to get precise information from others. And so this is kind of a conclusion that we have, namely something called the congruence principle, namely that the best way to communicate probabilities to others is in a fashion which is congruent or matches the nature of the event and the underlying uncertainty. So if someone tells you the chance of an abrupt drop in the market in the near future is 0.2348, it's weird, because this is an ambiguous event. We all know, based on our experience, that the markets are not lend themselves to quantification of this type. This is overly precise. If someone tells you, here's a deck of cards, and the probability of randomly selecting a red card is quite high, is equally disappointing, because it's an unambiguous event. purely quantifiable, you would expect to see probability that matches. And so these are a couple of papers basically showing not only that it works, but people actually sensitive to that. And people don't necessarily always like precision, as some people sometimes say, but people actually prefer imprecise information in cases where I think that is the natural level of precision for certain events. They find it to be more credible, more informative. So I'm skipping a bunch of details here and a couple of other studies. Let me say something about some work that Danny and I are doing right now in the context of climate change. So you have a scenario and you tell people about the fact that in California they anticipate the ocean level to rise, and therefore all the ports, Los Angeles, Long Beach, San Diego, will have to make adjustments, and they're looking at for predictions of how much rise in the sea level to expect over the 100 years. And you can imagine you go to two experts, and one tells you 20 and the other one tells you 40. I think this is inches. I can't remember the exact time horizon. Then you get to two other experts, C and D, and they both agree that it's going to be between 20 and 40. And you go to a third set of experts. One says it's going to be between 20 and 30. The other says it's going to be between 30 and 40. Now you go back to your boss and you ask him, so what did you hear? In each one of these cases, you can safely say, I talked to two experts. They agreed it's going to be between 20 and 40. But the 20 and 40 bounds here were generated, and they give you signals about the presence of a conflict, or no, not lack of conflict, but imprecision, or a mixture of the two. And it turns out that people are much more averse to conflict, top one, than they are to imprecision, presumably because they perceive that conflicts are harder to resolve than vagueness or imprecision. And here's a result when you ask people who've been exposed to all three of them to rate the various sources. And what you see, the red is the ambiguity, the imprecision, the blue is the conflict, the hybrid is in the middle. You see that in terms of accuracy, how easy it is to reconcile, how credible, how informative, how complete, in all these cases, conflict is perceived as the worst and the most aversive. I'm going to skip the various presentations. I want to say a few words about this, and then I'll stop. You know that the IPCC communicates for a variety of reasons, which you probably know better than I do. Uncertainty in terms of these phrases. This is a table that appears in the guide to the authors and reviewers, and the appendix or footnote to every single assessment and every single report. Basically, it's a way of legislating language. You know, right? Anything over 90% should be very likely. But we know that people, precisely because of many of the reasons I mentioned earlier, people vary in their interpretation of these words. They are subjective, they are personal, and it's very, very hard to legislate language. From this day on, likely means this and not that. So what we did, we've done some studies in the United States, but recently we completed a large international studies in which we wanted to test how people all over the world, when they read statements from the IPCC that involve these words, how they interpret them. And so we wanted to see if they interpret them as intended by the authors, whether they are interpreted identically all over the world in various countries. And we propose that a scale in which the numbers don't present just the words, but the words and the numbers together will do better. And there are some other issues I won't have time to talk about. So essentially what we do, we took 8 statements from the IPCC, two involving each one of these 4 words that you're seeing here, and people were asked to read them and to come up with their best estimate as well as lower and upper bounds, as intended by the authors. And then I'm going to, since I'm running out of time, I'm not going to show you all this. This is just some of the statements. But here, for example, if you are in one condition, the control condition, that's what you'll get. Since this is a sentence from the IPCC, it's very likely that hot extreme heat wave, blah, blah, blah. You are told, we're not asking for your personal opinion. I just want to know what do you think the authors intended to say. And then you move the slider and to say, I think this was at least 40, at most 60, and my best guess is somewhere in between. If you don't remember, you click, and the table pops out. So this is just like someone who picks up a report and, what do they mean by likely? Let me go to the appendix and then go back forth. And the alternative form, there's no, the words and numbers were presented together, and everything goes the same. That's just the only minimal change that was done. We ran this in 25 countries with over 10,000 people. So here's one key result. Let's look at very likely, which, remember, should be over 90. If it was over 90, all the distribution would have been above that line. Everything, well, for the most part, it is below. It's much, much more regressive, much more closer to 50%. Look at the huge variability. Very unlikely. Had people followed the IPCC prescription, everything should have been in this area. Actually, most of it is higher, close to 50%. The other thing that you can notice, however, is that these one in the alternative presentation are always pulled in the right direction. So lower for low words and higher for high words. So they.
What's the TMPN mean?
The translation versus verbal numerical. Yeah. What have I done now? So you see, I alluded to the fact that this basically spreads out the interpretation. So we calculated for each one of the countries the range of meaning. So that's the median assigned to various likely, to very likely, and the median to very unlikely under the two modalities, translation and verbal numerical. If it was the same, you'd expect things to fall along the diagonal. All 25 countries are above the diagonal, to different degrees, simply indicating that there's a much, much better spread between the words. Here is the rate at which, in which the best judgments are consistent with the IPCC mapping. And you see, again, consistently, this putting words and numbers together improves consistency with the guideline, especially for the extreme words, and that, again, happens for every single country. These are all 25 countries in our sample, and they are arranged in order how well they did in the control group, and so that's their level of compliance in the verbal numerical group, and although the order is not exactly the same, that's fine, but in every single one, there's an improvement. So not only is that help you, this minimal, almost cosmetic change in presentation improves ability to communicate accurately what you want to. But here's another thing. We are now comparing, different, that will be my last slide, yeah. Almost, okay. So we are comparing how well people from different countries understand to the same degree. So essentially so we have 25 countries, we have 4 words, so therefore 100 distributions, and we are calculating for each pair of these 100 things taken 2 at a time, a measure of proximity between the understanding of the word. So that, for example, we can calculate how similar is the distribution of likely in Korean and very unlikely in Japanese. And then what we are doing through this multidimensional scaling, we are mapping these words. And you see each one, so these are all the very likely, these are all the likely, and so on. So you have 100 points, different countries, 4 words. And you can see clearly some various clusters, one for each one of the words, and they are, for the most part, nicely separated, but, for example, here, they overlap. If you do the same thing based on the distributions that use words and numbers together, the clusters are much more homogeneous, much better separated, absolutely no overlap. So the added benefit here is not only that you can communicate better, that people understand you closer to the intended meaning, but it also that people from different countries understand much more similarly to each other the same statements. So I'm going to stop here, and I'm happy to answer any question about what I talked and about other things as well. Yes. Oh, okay. So that's what takes all my time.
So just to play devil's advocate, or just to kind of probe this a little bit further, what are the statements that actually end up in the media with the IPCC report? I mean, because I would assume that these likely, I mean, the likely statements are not, those are kind of technical statements that are the intended audience is largely government or other scientists. So, you know, what ends up in the media, and then it could be interesting to kind of look at what ends up there and then how the public perceives.
So it just so happens that just last week, Rob and I were at a workshop in Milano where, I forget his name, James, from Oxford University, right, on the Center for Study of the Media, and they're working. Huh?
He worked for the BBC.
He used to work for the BBC, right, yeah. And he did exactly these studies, and he pointed out that they looked at this and they said that the media tends to report the words, the terms, practically a large proportion, I can't remember, of the reports use the words likely or very likely as the content might be. And a minority, about a quarter of the cases, they also added a numerical interpretation to accompany them, but for most cases, they did not.
Okay, so they do actually, I mean, because they do take time to produce outreach materials, but...
The IPCC, you mean?
Right.
Yeah.
Right, but you are still finding that those kind of statements are ending up in the public's hands, and...
Well, I mean, you have, I don't know, I never did any studies of the media, but these people, for example, at Oxford did have a lot of studies, and they are following this, and they're comparing print media and television and so on. And then basically, I think he was saying that the print media was doing a better work of representing complete information than the television and so on. Yeah.
Thanks.
That's your record.
I was just going to say that. I mean, you didn't test this.
No, I did not.
No. But it's, given your results, it's not clear that when the people are writing their chapters, they're using the words consistent with the numbers.
Well, that's something that I always put. I always put this in a discussion. I wrote 2 or 3 papers about this. I always put in the discussion. No one puts questions. In other words, there's an assumption is that the authors are following the guideline. We don't have no way of verifying this, but my point is that if you're going to have, every time you write a word, you also have to write the numbers close to it, that will also serve as a reinforcement and reminder to the author. That's a secondary benefit. Yes. Yes.
Can you go back to the slide that has the 3 types of experts, and the opinions were between 20 and 40?
Which one?
It was the 3 types of experts in conflict, the vague response. And
yes. Oh, yeah. It's not 3 types of experts.
Yeah. 3 types of responses.
Right.
So, I guess the way I would interpret
You want to see the slide with the results?
It was, you were describing, this one.
Yeah.
So the conflict case, if I were interpreting this, I might put, since it's an uncertain term, I might put my own range around 20 is really between, maybe they think it's somewhere between 10 and 30, and expert B thinks it's somewhere between 30 and 50. Whereas the vagueness, since they both say it's between 20 and 40, maybe I interpret that as, well, maybe they both think it's around 30. In the hybrid case, expert X would have kind of a best guess around 25, and expert Y is 35. Is this, but then that wasn't kind of part of what you're finding.
Well, I mean, I didn't present you all the findings because Danny still hasn't finished data analysis. but I'm just giving you some of the finding, and I'm telling you the finding. Oh, I see what you're saying. You're saying that basically that your intuition of how you would interpret this did not match the way our participants judged this.
Yeah.
Just sort of comparative ratings on these characteristics across the bottom, but we also have data on people's best guesses and their best guesses to the lower and upper bounds of the true value. And we see much more consistent ratings in the ambiguous or vague condition than the conflict. So we see more biasing based on the expert projections that were shown when there's the conflicting information. Which may possibly support what you're saying. But so, they're looking at quantitatively equivalent information in aggregate, and there's more biasing systematically when they're in conflict versus otherwise.
I mean, the point I was trying really to make is, regardless of the direction of the results, much more the fact that there's a lot of information about how things are being communicated and about the scenarios and the mental models that people build about what do these numbers mean and how should I interpret them than just the numbers. And I think that that was the key point I was trying to make. Yeah. Yes.
Back to the IPCC study, I have a couple of quick clarifying questions.
Yes.
So in the verbal numerical presentation, does that mean it gives you the word like likely, and then immediately afterwards it gives you the official numerical translation?
Yes.
Okay, and then the probabilities that participants are giving, is that supposed to be, if I'm a participant, am I supposed to say my subjective probability for this event in light of the information I just got, or am I supposed to say what probability are they trying to communicate to me?
Okay, I'm glad you asked this question because that gives me an opportunity to present one more slide, to sneak in one more. Okay, so what we are asking them really to give us what do you, to clearly state that not what you think, but what do you think the intended meaning.
Okay.
Having said that, that's a two-sided, it's a two-way road, right? I mean, you tell subject and they to do what you want, and they do what they want, okay? And here's a slide that was not part of the international study, but part of the previous US study, when we break down the numbers assigned to the various words by party affiliations. These are the interpretation of people who declare on a 7 scale are 6 to 7 Republican, and these are people who are on the same scale 1 to 2 Democrats. So on average, you see that people who say, I am a Democrat, assign probabilities on average 15 points higher than Republican, which to me alludes exactly to the question that you have in mind. So you may think that you are the IPCC and you have the authoritative science and you give basically like God's giving from Mount Sinai. This is the probability and that's how you should follow. But people have their own beliefs, they have their priors, and what they are getting, just as you said, another piece of information which may cause them to adjust, and not everyone will adjust to the same degree, and that will not yield, of course, uniform perception across everyone. So that's, I think, that's exactly what happens. That's another thing that everyone who communicates needs to be aware of, that by saying the probability is 0.9, for most cases, people discount this to some degree and put in the context of everything else that they believe and don't necessarily act as if it is 0.9.
What led me to that, ask about that distinction, was just how little the verbal numerical helps. I mean, you're telling people, right, I mean, it's likely, and by that I mean exactly this probability distribution, or this probability interval, and then people immediately give you a totally different interval.
But these are different people. But so the variance is between many people. So some of the people are Republicans, some people are Democrats, and some people are men and some people are women. And I mean, I didn't have a chance to say, but we are also showing that things how much do you believe in climate change, how much experience you have in climate change. All these things are somewhat correlated. So part of the huge variance that you see is pre-existing variance among participants.
David?
Yeah.
It's also worth saying that each of these statements, you write on the microphone, please? Noting that each of these statements is attached to a specific statement about the world.
Yeah.
You know, climate change will do you in. You know, things like that. And so people are presumably sorting what likely and unlikely means in the context of the consequences of the statement to which the verbal description and numbers are attached to. So
that's another thing that, you know, in work on probability words was found. In other words, that the interpretation of the word is associated with the base rates of the events. So if you ask people, what does likely mean in the context of a severe snowstorm in Colorado, and what does likely mean in the context of, you know, you going to the doctor and telling you something, people get you different results as a function of of how rare or frequent the thing is to begin. Yes. Oh, I'm sorry. Maybe I have to stay out of this.
Yeah, I was wondering about on the study you showed how they answer the question and then they have the choice where they can hit the button that shows the actual table with the IPCC terms and the numerical representations of those. I was wondering if you happen to track how often people used that and if that might say something about like their confidence.
We did. We spent a lot of money working that was there's a kind of a JavaScript into Qualtrics. It costs a lot of money to implement. So we better analyze it. So yes, I think so on average what we found is that it varied across countries, but on average, people click this button 1.5 out of 8 times. So there were 8 items, so on average, there was 1.5. For some countries, it was lower, some countries, it was higher, but that was basically, yeah. So people, at least once, almost everyone did.
Did it have any bearing?
No, not really. Yes, I'm sorry, yeah.
What your views are on the case in Italy with the case of the earthquake and the scientists that were convicted. Are there any lessons learned? Do you think that how they, I'm not perfectly familiar with all the details of the case, but the scientists were accused of not communicating the risks in an adequate way.
Well, I mean, I know about the case, and it's a very troubling case. It's a case, those of you who don't know, it's about an earthquake that occurred in a place, and there were risk assessments that they were not as extreme as some people thought they should have been, and then the people were actually tried and found guilty. The answer is I don't know, because other than what I read in the New York Times, I don't know exactly what was communicated and how it was communicated. I mean, all you can say about this kind of judgment is to really point people to the calibration curve or the equivalent of the calibration curve. I mean, I think that what you need to be very, very clear when you're communicating is that you're making predictions about stochastic and not deterministic event. That there's a probability that you're being wrong, and you're basically trying to quantify your probability. And even when you say it's 80%, there's an 80% probability that will happen, that will only be 80% of the time. So people should expect you to be wrong 20% of the time. And I think, in the decision theoretical community, the idea is you do not judge decisions by the outcome. So in other words, if someone gets an extremely rare complication because of a medical procedure and something terrible happens to them, but it only happens in one of 500,000 cases, you don't judge them by the outcome, but you judge by the adequacy of the procedure as it was implemented based on all the information that was available. So I think there's a mismatch between maybe what experts on probability, experts on the one hand, and the public expect. People refuse, I think. I mean, that's an oversimplification, but I'm going to say it anyway. People are don't like the idea of things being uncertain and being stochastic. And they really would like them to be all deterministic, and they would like all uncertainties to be eliminated and reduced. I think it's very important when you're communicating about things that you think are important to give people the right kind of level of expectation about what is the level of irreducible uncertainty. No matter how much time and how much money and how much effort we are going to spend on this particular problem, we'll never be able to, at least in the foreseeable future, to reduce the uncertainty below a certain limit. And so not to have people have unrealistic expectation of what predictions can be. So I don't know much about that case, but that's the general principle that I take from there.
So I really enjoyed your results about the IPCC.
I found them depressing. I'm glad you enjoyed them.
Well, I was going to say that I think that to a certain extent it highlighted for me how being a social scientist working on this issue is sort of a masochistic exercise.
I didn't go that far.
But it is just sort of painfully in line with what you would kind of expect based on how people perceive things. And I was wondering if there's been any research done on sort of the higher certainty statements that are made in the IPC documents over different iterations. So what I'd like to see would be, well, if we're saying virtually certain, how do people interpret that? Mm-hmm. And then how does that differ from the terminology we used in previous iterations of these documents? Yeah.
So the reason in our study we only use those 4 terms is that we picked sentences. We wanted to pick sentences from the report, and we picked from AR4. And AR4, most of the sentences, I mean, these 4 words accounted for the vast majority. There were very, very few uses of extreme words. So that's what we didn't study. So, but I think I agree with you. It'll be very, very interesting to do this study. But that's also a good point to bring up another troubling issue, is that lots of the things that we've done and we understand, about eliciting probabilities, communicating probabilities, much of this breaks down in the very, very high extreme. It's very, very hard. I only have to read a little bit about, the shuttle disaster where, engineers got confused between 10 to the minus 4 and 10 to the minus 6, right? So when it comes to that extreme, it's extremely difficult to elicit probability, to get precise judgments, and to communicate with other people very, very precisely or accurately, this kind of thing. No, I don't know of anyone who's done a study of this work, but I can tell you that our results here are very, very general. So in the sense that it has nothing to do with climate change. I have colleagues who have done similar studies with people who work for the CIA and for intelligence, for the British Intelligence Agency, and the kind of likely meaning, everything and the kitchen sink, you get the same thing with analysts in all these places, and so professionals and so on. So that's not something it's not something unusual.
Right. I have 2 questions. The first one, so you talked about how people like to have a lot of quantitative information, like they want you to be precise,
right?
And how you should have the event and the probability the word be consistent. But for example, I don't know, I find it that it can actually be very, in a way, useless, and at least in terms of my field of study. So I work with drought, for example, and I can tell you that there is a probability of 0.5 that soil moisture is going to be below 0.2. Look, what is,
the probability?
That soil moisture is going to have a certain value, like say 0.2. But what does that even mean to a farmer? Like, it makes more sense for me to talk about drought than talk about like soil moisture being below 0.2. But then I can say, if I define drought in a given, like, how can you communicate that to stakeholders in a way that's more meaningful than say like a very arbitrary and maybe technical that doesn't really mean anything, right, but at the same time that it will make like carry information. Second question is, from the IPCC study, if I'm interpreting correctly, I have 2 conclusions. One is that people, scientists and media have to be careful with the language that they use, and second is that people in general don't know how to read and follow directions. So the question, one of the questions is, what is driving, what cognitive processes are driving people to not, to not do what they're asked to do, and also, but it's related. It's like part B of this question. Okay. As a scientist, I say that's interesting, but if I'm a politician, or if I'm like, if I have an agenda, how can I leverage that to?
Well, okay, so let me start at the end, because I remember, I forgot number 1. I think you're right. You are right that probability words, because they serve a role because they are imprecise, and language is imprecise, and because it serves roles that we want in daily life, and they are imprecise and they can be easily manipulated in a self-serving way. So there's a true story. It's by now mythology, but it was documented in many books, that in the debriefing after the 1962, 63, I can't remember, invasion of Cuba by 61. Okay. So in the debriefing, again, the CIA said this is likely and so on, and it came out one day, well, we said likely we meant 50 to 60, and the politicians, likely we understood to be 80 and 90. In each one of these cases, clearly they were exaggerating to distance themselves from the disaster. And I've worked with a couple of people in accounting, and they ran experiments with accountants, and they were told, you have to do an audit and write a report. And in some cases, they were told, and to use these words, they have a list of words, similar words. And in some cases, they are told, what we want to do is the best, most accurate, most unbiased report. In some cases, this is a valuable client. We want to do it quickly, and we want to be helpful to the client. And so in the two conditions, when they use the same words, and the numerical values that they assign to them are exactly what you would expect. In other words, people adjust them in a strategic, and I don't know if conscious or unconscious way, in the direction that is. So clearly, a politician or a stakeholder could interpret these words in any way that they wanted. So if likely means more than 66, you can say, likely is 66, or in the environment, or say, no, likely can be anything, so point attention to the higher words. What goes on here is, I think, a combination of many factors. It's not just one thing, and I'm not sure it's a bias. One is, as I said earlier, I think that people are interpreting these statements in the context of what they believe and what they know or they think they know. That's one thing. Secondly, I think that the IPCC selected these numbers in a way which is suboptimal, in the sense that they could have selected the threshold for what likely and unlikely means in a way which was more consistent, in which most people use these words in the language, and they didn't. So in other words, you saw exactly how very likely and very unlikely, how inconsistent they were. They really are, because that's not the way people are using in the right world. And I think there's a general phenomenon, which is the following, is that when there's a two-way communication from an expert to an audience, and people provide numerical information, when received from sources is typically discounted to some degree, because you never, unless you know exactly who that person is and so on, say, well, yeah, maybe they make an error, maybe there's unreliability and so on. So all these things, I think, in this case, kind of work together in order to bring these results about. And I think that this discounting is even more extreme in cases when there's something that you know relatively little about. So I think that that's a combination of all these. But I honestly don't remember your first question by now.
How can you communicate, like when you're talking about extreme events, extreme climate events, such as drought? I mean, people know what drought is, but people don't know what a solar moisture 0.2 means. I mean, it's even, yeah.
Well, I mean, I agree. I think it's really very hard, and I think that it varies from one domain to another. So I was telling you about this example, which I just mentioned. Well, let me now say a few words about this experiment, which I just mentioned in passing. So we paid attention, a colleague of mine who was an accountant paid attention to the fact that when management issues forecasts of performance of their firms, how much that will be earning per share for the next quarter or the next year, they could say 6 cents or 7 cents, or they could say between 10 and 20, that the vast majority of the reports were imprecise. Okay, so you wonder, here's a situation where everything can be then verified, because how can people get away with being imprecise? And it turns out that when you run an experiment and you present the same, here's the description of the firm, and this is their press release about what will happen next quarter, and the only thing you change, whether it's going to be 6 cents or between 2 and 8 and so on, that's the only thing that you manipulate. People are actually more likely to buy, to say, I'm going to buy this, the imprecise one, and they say, this I find to be more credible and more rating. And my interpretation of that is that people think, that is the level of precision I expect in this environment and in this context, okay? And therefore, if someone is trying to be very, very, very precise, I find it hard to believe, and therefore I dismiss it. But that's not the answer to your question, just by background. I think the answer to this question is that when you work with people, you try, especially a sustained relationship, for example, of this type where we make periodical forecasts, you try to build, you have to teach them how to interpret these things like 50% and 40% by putting them in the context. In other words, you always should try to find what are things that people are living with anyway, and they are very familiar with, and they have 20%, 30%, 40%, and so on. So you say, this is an X% probability, which is basically in the same category, in the same ballpark as those events, and so on. But that's about the best I can answer.
Time for 2 more questions.
Can I go? So I have a question about this particular slide in this study. So when you were transitioning between the translation and verbal numeric, between these three groups, did they...
Two groups.
Okay, the two groups, did they shift up by more or less similar magnitudes, or did the...
What do you mean?
Like when you actually had the two different variations of this, did Democrats have a greater magnitude?
The Democrats and Republicans?
Yeah, or did maybe the Republicans shift up by a greater magnitude because they were originally more
I see. Now I understand the question. Okay, so I don't remember the exact details, but so the question was, so there's a beneficial effect that I'm documenting for having words and numbers together rather than just words. And I think that you're asking, is this an effect that holds for all subgroups? Does it work for Republicans and Democrats and so on? And I don't remember if it worked exactly the same, but we've never seen a subgroup or a subset of respondents, not any country, not any subgroup, not people who are high numerate or low numeracy and so on, in which this manipulation was not effective. So it worked in the expected direction for everyone. I don't remember if it everywhere to the same magnitude. Does this answer your question?
I have one over here.
Yeah, okay.
So I'd love to hear your thoughts on how you might capture group preferences rather than individual perceptions.
Group, okay.
Because, I mean,
in what context are you asking this? Give me...
So I'm interested personally in how you can measure a community's preference for one protection measure over another. And it seems as though you can't necessarily aggregate individual preferences. So I'm looking for survey methods.
So are you asking a question about building a social welfare or a social preference?
I mean, it could go in the direction of willingness to pay, but just what their preference is for a dike versus nourishment or methods that people are more accustomed to versus something new.
I don't know. I'm happy to talk to you about it. I have to think about it a little bit. I saw that. Yeah.
So my question is very quick. So you talked about text and numbers. Can we just use numbers?
You could use right number, but that will be wrong. Because think about. There are two arguments. One is the argument which I try to make about the congruence, and I think that using numbers in most cases will be an over-precision given the level of knowledge and that people have, or the level of consensus between the various people. So that's the one thing. And I think that that's exactly the reason the IPCC went the way they did, because it would have been much easier for many people to say 60%. But if people sitting in a room say, "What do you mean 60%? I think it's 40. I think it's 35." So in other words, the disagreement among experts themselves has to be captured. So I'm not saying they did the right thing. I think that they selected. They went in the ballpark in the sense that they selected something that communicates the level of imprecision and lack of complete confidence in the estimates. But I think what they need to do, now that they've established that, you need to fine-tune it in a way that will make it more in line with how the people will read it.
Okay, I think we're going to have to wrap it up there. Let's thank David again for a very rich and fascinating presentation.